Datasets that we work with are often highly dimensional. This could be either in terms of the number of observations or the number of variables that we have. This week, we're focusing on the number of variables. Having a large number of variables is both a blessing and a curse. If we have high dimensions, it means we have lots of information about our data. Unfortunately, there are also several downsides. Some models don't work well with a large number of variables. Using a large number of variables could increase computational time required to analyze our data. And including an excessively large number of variables in our modeling drastically increases the complexity, which is generally advised against. As statisticians, we try to stick to the principle of parsimony. This means that we want the simplest possible model that adequately describes the data. For this reason, we often employ dimension reduction techniques. There are many, but this week we'll look at PCA, or Principal Components Analysis, and MDS, or Multidimensional Scaling. Principal Components Analysis, or PCA, is a dimension reduction technique. We take linear combinations of our existing variables to create new variables, such that our new variables do a better job of explaining the variation in our data, if we take a subset of them, that is. Note that for this reason, we can only perform PCA on our numeric variables. Based on the data in this image, if you had to pick a set of orthogonal axes that best explain the variation in the data, what would you pick? Would you pick the standard x and y axes, or perhaps something slightly rotated? It turns out that the axes we should choose are the eigenvectors of the covariance matrix of our data. To determine the order of the axes, we order the eigenvectors by the magnitude of their corresponding eigenvalues. The example shown here is just using 2 dimensions, of course, but you can extend this idea into higher dimensions. An important note: when we perform PCA, we will end up with the same number of variables that we start with. I know what you're thinking. How is it considered dimension reduction if we end up with the same number of variables? Well, it is true that we end up with the same number of variables, but we can then use this information to reduce our dimension by picking the variables that are the most important. Our first principal component explains the most variation in our data. Our second principal component explains the second most variation in our data, and so on. If we use a scree plot, like the one shown here, we can actually see the proportion of the variation in our data that each principal component is able to explain. For example, in this picture, we can see that 60% of the variation is explained by the first PC, and 20% is explained by the second PC. The remaining PCs do not explain very much of the variation. Therefore, it might be reasonable for us to eliminate PCs 3 through 7, helping us reduce our variables from 7 down to 2. Multidimensional scaling, or MDS, is another dimension reduction technique. It allows us to map high-dimensional data down to a lower dimensional manifold. With MDS, we're concerned mainly about preserving the similarity between observations. For example, if 2 observations are very far apart, or dissimilar, in 5 dimensions, then we want to make sure that they're still far apart when we go down to 2 dimensions. Similarly, if 2 observations are very close to one another, or are very similar in 5 dimensions, we want to ensure that we keep them close together when we reduce them down to 2 dimensions. In order to do this, we need to have some way of measuring the similarity between 2 observations. We do this using some kind of distance metric. There are many different ways that we can define the distance between 2 points in p-dimensional space, and I encourage you to type $dist in the console in RStudio to view the documentation for the dist function, which lists off several different distance metrics. The default that this function uses is the Euclidean distance that you're probably used to. When we do multidimensional scaling, we start with observations in p-dimensional space and the distances between every pairwise combination of the observations. We'll let d sub ij represent the distance between the ith and jth observations in the p-dimensional space, where I does not equal j. Note that, in some cases, we might not be given the observations themselves, and we might just have access to the distances between them. We can still do MDS if all we have is the distances between each pairwise combination of the observations. After performing MDS, we end with observations in k-dimensional space, where k is less than p. So how does this actually work? Well, we need to define some kind of function that will allow us to minimize the difference between the distance in the pth dimension and the distance in the kth dimension for every single pair of observations. Take, for example, the Kruskal-Shepard scaling. Here, d sub ij is the distance between the ith and jth observations in the pth dimension, and the part I'm highlighting here is the distance between the ith and jth observations in the kth dimension. Ideally, we want this part to be 0 for every pair of observations we have. This is just one possible scaling, so please check the notes for other examples. You might be wondering what MDS is used for. There are lots of interesting uses of MDS, but one that's particularly neat is the designing of user interfaces. For example, MDS can be used to optimally place the buttons on a website such that the buttons that are most commonly clicked together are placed near one another on the page. In the notes, we saw an example of MDS that recreates the map of Europe using just the distance matrix in R called Eurodist. You might be wondering how this is an example of dimension reduction. You might be thinking, wouldn't we have started with coordinates in 2D and also ended up with coordinates in 2D? This is a really good question. Based on the way that we would normally think about it, such as if we're looking at a map, the distance between two cities is two-dimensional. However, when we consider that the Earth isn't flat, we're really looking at three-dimensional coordinates, and MDS helps us map these 3D coordinates onto 2D space. With the map example, these cities seem to magically line up with their true locations on the map of Europe. You might be wondering if this always happens, or if the cities could have been slightly rotated. The answer is that they could have been slightly rotated. With MDS, we're more focused on preserving the distance relationships than we are about preserving the orientation.